read on the 50 most important ones. So what were those design decisions? I start with milestones, and namely before 1970, when Thomson and Ritchie, McIlroy and Osana made this, created their work on the PDP-7 edition. Remarkably, this edition of Unix, you see here the form that it was found, printout with handwritten notes, consisted of about 20, the kernel consisted of about 2,500 lines. As Steve Johnson quipped, I once heard an old-timer growl to a young programmer, I've written bootloaders that were shorter than your variable names. Despite this diminutive size, this kernel featured the layer and partitioning as an architectural feature. So you see here various commands and the s.1 s.star files being the kernel. The commands call the kernel. The kernel does not depend on the command, so we have clear partitioning. The commands are not coupled together, and we have additional partitioning through file naming conventions. We have a process management with a fork system call. Descriptor management, here you see calls to get a descriptor and put a descriptor back to make it available. This is used to allocate them for reading and writing. We have separation of file metadata from file naming through the inode abstraction, which is still with us today, and still some other systems do not support this and do not, for example, allow us to rename a file while this file is being used. We have devices as files. Here you see the names of some of those devices in the source code, such as TTY in and TTY out. A file IO API, which is still available today. A file system API, very primitive, not even hierarchical directories, and even an interpreter, a feature that has stayed with us. Here, two system commands, indent and lcase, lowercase convention, were written in a relatively high-level language, namely B, which was implemented through a threaded code interpreter. The first system that was actually called Unix was running on a PDP 1120 computer, such as the one you see here. And here you can see the architecture diagram of this edition. Try to keep this in mind because it will become very important later on. You see it being partitioned on user space and kernel space, and we have a system call interface, an IO subsystem, process control subsystem, kernel utility functions on the lower left, and the commands are split into user commands, administrator commands, all being based on a library, everything written still in assembly language. So here we have a binary API with based on numbers. So exit is system call 1. And remarkably, on the right, you see the same system calls with the same numbers on FreeBSD 11, so a very modern Unix system. And you see that these are remarkably have lived up to now, which is, shows how the architecture has persisted through so many years. And many system calls are, most system calls are available with even the same numbers on Linux. We have the shell as a user program, so the users can select the shell. At the time, users in other systems were given one shell and couldn't choose it. We have the abstraction of input output, no pipes, but we could direct to and from programs. We have interoperability through documented file formats. So formats were documented and programs could read and write on those programs. And you see here clients of specific file programs. And this also gives us an important idea, convention over configuration. So there is no API, but specific programs know how to use a specific file format and are communicating through it. We had user contributed tools and games located in a directory called /usr for users. With an interesting thing, if somebody didn't document it, the cron program would go there and remove it at night so that users would get into the idea that documentation is good. USR is still with us today, but of course not for user programs, but for programs that are not needed at boot time. We got a tree directory structure with 2 system calls and the number of programs that use them. You see them on the right. A mountable file system interface. All this on the first research edition of Unix, still written in assembly language. The second research edition brought with it a software library with names that you recognize even today. The third edition brought something extremely important, namely pipes and filters, based on ideas that Doug McIlroy described in 1964. So it took almost 10 years for these ideas that you see them described in this 1964 memo to be implemented in a usable form on a system. Once they were available, people got enchanted from them and started overnight converting most programs into filters. The fourth research edition, 1973, was implemented in a language called New B, and it brought structured programming with it. It had about 6,300 lines of New B and just 700 lines of PDP-11 assembly. So most of the system got implemented in a higher level language. And this gives us about 100 functions and 50 assembly language symbols for the kernel, rather than 250 global symbols in the first edition. So although the system was a lot more functional, offered more functionality, it was more structured than its predecessor thanks to this New B programming language, which you see is on the right, looks remarkably like C. With it came a language-independent API. You see here the same system call documented both for assembly language on the top and with as a system call for C on the bottom. Data structure definition and reuse through header files. Previously, people were copying the definitions from the documentation. Dynamic resource management through something called malloc, which here allocates maps, things on the map rather than memory. A device driver abstraction with special files documented here. The names are and the devices do not longer exist, but the abstractions live on because we have a driver interface based on a so-called strategy to queue interrupts, and exists on modern editions of Unix and even on Linux. So here you see something like an object-oriented interface where you have pointers to functions to open, close, read, and write things associated with a device. We have a buffer cache. Again, this has lived until today. You see here the constants on the left on the 4th edition Unix, and on the right the same constants with almost similar names defined in FreeBSD 11. The 5th research edition brought with it command files. Here you see a shell script that compiles some of the user files. The 6th research edition is interesting. It was the first documented by John Lyons at the University of New South Wales in Australia. It was one of the most photocopied instruction manuals for students. And it brought with it the portable C library. Most of it is available today. The 7th research edition, some claim it's an improvement not only over its predecessors, but also over its successors, brought with it an important idea, the idea of Unix as a virtual machine. So Steve Johnson recounts that Dennis Ritchie said, it may be easier to port Unix to a new piece of hardware than to port complex applications from Unix to a new operating system. So that they decided that would use Unix as an abstraction, move it to several machines and have applications run like that. It also brought dynamic user memory allocation, the stdio library, static analysis through lint, environment variables, again, another case of using convention over complicated APIs. They're used for many things, such as the kernel, the shell, and the C library. Language development tools in the form of the Lex Canalizer generator and the YAC parser generator, and immediately 12 programs were based on them: awk, BC, the C preprocessor, egrep, and the others you see here. This also brought a number of domain-specific languages. I list here many of them, so many languages that are available under Unix. We got a documented file system directory hierarchy. Again, this has lived until today. Another case of convention over enforcement and also adopted by other systems such as Linux. Importantly, the documented hierarchy contains parts of a self-hosted system, so source code, development tools, libraries, and documentation. After the 7th edition, Unix moved to Berkeley, so Berkeley started developing systems there. The first Berkeley software distribution wasn't a complete system. It's had some software packages such as the C shell, X, Mail, Pascal, and termlib. FreeBSD was the first system that was complete. It included virtual memory paging, very important. About 2,800 lines out of the 1,600 lines of the kernel were devoted to it, and the new system calls that you see on the bottom. FreeBSD, still distributed on tape, gave us a regular expression library, which had at the time 5 different implementations, but it struggled to get adopted. This is an important lesson for the architects among us. Just one client more, and by 4.3 BSD, just 2 more, DBX and RDist. In FreeBSD, it's used for more programs, ed, grep, sed, and x, but it was a long uphill battle, its adoption. It also offered us optimized screen handling through cursors and termcap. These were used to allow programs that could run on teletypewriters and on glass terminals. Nowadays, it's used for a different purpose to allow us to use terminal emulators. 4.2 BSD brought the Internet Protocol Library, inter-process communication, abstraction for database access, for accessing network interfaces, and the pseudo terminal driver. You see many new system calls that were introduced at that time for all those facilities. 11 system, a number of system calls you see on the right used by 2 library functions, 11 system daemons, and 8 user mode programs. 4.3 Tahoe offered multiple CPU architecture support and time zone handling, important because it was a community distribution. So we see now communities contributing to Unix. Rhino implemented the kernel packet forwarding database in the virtual file system interface. So the abstractions I showed earlier moved up to the file system interface. 4.3 BSD, it gave stream IO functions. Again, a very interesting abstraction, but very little used despite its importance. 4.4 BSD, stackable file systems and the generic system control interface. And with 386 BSD, we have releases that were done by volunteers through a magazine called Dr. Dobbs Journal, and William and Bill Jolitz, who created an open source system based on the code that was available from Berkeley. Based on that, a number of volunteers, because things were not moving forward with 386 BSD, organized community contributions. So we have Unix moving from an open source software, as was done with 386 BSD, to an open source project with people organizing patches with metadata. And out of that sprang one important system called the FreeBSD. With 1.1, we had a package manager. With 2.0, a process file system and dynamically loadable kernel modules, which allowed many more modules to be implemented and loaded only when needed. By now, we have almost 1,000 such modules used for all things such as device drivers, file systems, emulators, system calls, and so on. 2.1 brought Linux emulation, a packet capture library. In 3.0, we have a common access method subsystem for accessing various peripherals, storage peripherals. And you see here something interesting. This has its own architecture. So it has layers on top of the peripherals, a transport layer, and the hardware abstraction layer on the bottom that has specific device drivers for abstractions such as 1394 or the fiber channel or iSCSI. 3.4, another large system was brought in, the graph-based kernel networking and user library. Again, here you see a mini architecture with the network protocols being between the socket and the net graph. 4.0, OpenSSL, introduced OpenSSL, 1100 line files, 700,000 lines, jails to isolate process and its descendants, and access control lists. With 5.0, we got symmetric multiprocessing, modular disk I/O request transformation framework, GEOM, another architecture you see on the right, mandatory access control, and a pluggable authentication module. With 5.3, streaming archive access library and a mini port device driver. 6.2, basic security module auditing. By 7, ZFS file system and storage pools came over from Solaris, and dynamic tracing also from Solaris, very interesting technologies. By 9, paravirtualized I/O, InfiniBand support. This sounds small, it's a huge system, and application compartmentalization. FreeBSD 10 introduced virtual machine monitor, beehive, and user space raw packet processing. 11 introduced network blacklisting. Let's pause here and try to think if you have seen a trend through this evolution, through the various things that I've described, especially during FreeBSD. If not, let me give you some quantitative results. How has the system evolved in terms of volume? If we look at the user commands, they have evolved, as you see, at a fairly constant rate throughout the various releases, from about 50 commands in the first edition to about 700 commands in a modern FreeBSD system. If we look at system calls, they remained constant through the research systems developed by AT&T. They increased when at Berkeley, and then they remained stable again. And then we see a constant increase under the FreeBSD edition. So 3 different distinct phases in their growth. Probably in the open source world, for example, people want to leave a mark, and by perhaps introducing new system calls, whereas in stable communities such as AT&T and Berkeley, once they did their work, they stabilized. If we look at C library functions, very modest growth initially, and stability, and again a rise in the FreeBSD versions. In devices, we see a constant growth, which is natural given the evolution of hardware. We see that the growth in documented file formats has stopped. Probably things nowadays have become so complex that documenting a file format for interoperability is not enough. We need a proper API. This facility is probably no longer serving us. We see a constant growth in the system commands, which is to be expected as systems become more complex to administer, and also in the kernel interfaces. Moving to cyclomatic complexity, we looked at the mean cyclomatic complexity of the Unix commands, so the code associated with Unix commands, library, and kernel, and we see this V shape, which make us think that maybe there are some forces acting on it. As it rises, then maybe some forces make it fall, and could be attributes of the implementation of corrective measures. And we looked at it also on the Linux kernel and the GNU library and the user level commands, and we saw similar trends. So this is something interesting. The same forces could be at play on Linux and GNU systems as well. Based on these qualitative and quantitative findings, we tried to put together a theory of operating system architectural evolution. So how it moved from the early days to the modern ones, perhaps from a cathedral style to a more communal style of working. One has to do with the form and pace of architectural evolution. And what we see here is that many core architecture decisions are taken at the beginning of the system's time. So look here at the timeline of things that I have described in the history. and see how many things were done at the beginning and how fewer were done later on. And in addition, we see that most architectural decisions survive over the system's lifetime. So here I've put lines for each decision, and you see that many that were done at the beginning are with us until today. Very few were done and then removed. About 12,000 facilities have survived for more years, so about 17% of them. More dramatically, remember this architecture picture I showed you from the first research edition Unix. Pay attention to the colored boxes. Now, squint your eyes and allow me to show you the architecture of FreeBSD 11. Most of those things are at the same place with the same color. And what this tells us is that architectural form has largely remained stable, especially in the areas where technologies haven't evolved, which is the case, for example, for multiprocessors or the input-output subsystem. So based on this, we can say that new architectural decisions are continuously made, further fueling architecture evolution. So you see here that we have more things done after the initial architecture was put in place, but these have stayed with us. So architecture is evolving, it has not remained stable. However, the rate of architectural decisions declines over the system's lifetime. So in the first 20 years, we have identified about 40 such decisions. And you see another 45 from 1986 until 2000. We also have witnessed an accumulation of, regarding the accumulation of architectural depth. We have seen some evidence of it. So we have seen architectural decisions offering features that are either similar to existing ones or remain underused. So for reading now, we have a system calls such as read, pread, readv, preadv, receive, receive from, and receive message. We have 4 ways to log things. So we can log to var log, we can use syslog, we can use act and audit D. We have both the user group other permissions and ACLs and mandatory access controls. And both threads and processes are used for multitasking. So these are things that are similar to existing ones. The clarity that existed in the first edition is no longer there. However, we have also seen that depth is systematically paid back despite the increasing system size and complexity through these V-shaped figures, as I showed you earlier. Looking at the forces of architecture evolution, we have seen that convention, instead of enforcement, facilitate the evolution by reducing effort and offering flexibility. We saw that through the use of text files, through a directory hierarchy. It's not prescribed through an API, it's there, and we can add directory hierarchies as we wish, through documented file formats and through environment variables. As another force, we saw that portability, because it's very complex to move a system from a PDP-11 to a VAX, to a Spark computer, to a 386, is a key driver of architectural evolution. In addition, we saw that the ecosystem of other operating systems and the third parties constantly shapes the architectural evolution. Remember the picture I showed you on the left regarding evolution. Although systems did not evolve independently, they fed back into the orange systems that we saw. In addition, we saw many major third-party subsystems in FreeBSD 11, systems with 3 million lines of code, such as LLVM, or 1,500 million as a GCC, or 1 million as bin utils. And we see also considerable influences by other parties, so not projects, but parties such as the Trusted BSD project, NetBSD, OpenBSD, Kame, SemiHalf, Dragonfly Linux. We see thousands of commits and lines of code introduced through those third parties. So we can see that, and we can say that third-party subsystems facilitate evolution through code reuse, but also they add technical depth. How is that? large subsystems form their own independent architecture. So for subsystems such as NetGraph, SSL, MAC, PAM, the pluggable authentication module, GEOM, BSM, ZFS, and Ztrace, each one of them has its own architecture federated in the larger architecture. This is something important. It's perhaps a way in which architecture evolves once the system grows a lot. And it's another force that we have seen in the evolution of Unix, perhaps the most significant one in modern Unix. Dear colleagues, this brings me to the end of this description of the form and forces of Unix architectural evolution. Thank you very much for your interest.
All
of
right.
course, open to questions.
Thank you very much, Diomidis. It was super interesting. I'm seeing some questions popping up in the chat. There is one by Olaf. Olaf, if you want, you can ask a question directly.
Good morning, Diomidis.
Hi, Olaf. Nice to hear you again.
Fascinating work you've done there. It's amazing. I've had a look at your repository. Amazing. Thank you very much. Very important contribution. So my question is, looking back, assume Koenig, Ritchie, Thompson, these guys are doing a retrospective. Which decision or decisions do they regret the most? What would they do differently these days?
Right. On a less serious note, one thing they have said is Ken Thompson has said that he would name the create system call, which is spelled create without an E at the end, one with that E. I think what would they have done differently can be judged more than this by looking at the systems that came after Unix from the same team. So Plan the 8th and 10th edition Unix and Plan 9. I think they would have wanted the tighter integration and expanding the idea that everything is a file. So in systems that followed from that team and not on systems that are based on Berkeley, Unix, and the modern open source variants, we see that network abstractions are also available as files. We see that they are trying to bring under the same roof also multiprocessing and graphics. It has not caught on. I'm not sure if this is because they were facing an uphill struggle with systems that were more widely adopted, or because of inherent limitations of that architecture.
All right. Olaf, are you still there?
I'm still there. Yeah, thank you very much. Good one.
Thanks, Diomidis. I'm noticing in the chat that there is a nice discussion going on between Yasmin and Owen Woods. It's about architectural decisions over the lifetime of the system. Yasmin, if you want, you can trigger this discussion and include also Diomidis.
So that was just my observation with respect to one sentence. The rate of architectural decisions declines over lifetime, and in at least my experience, this is a bit contradictory with what we do usually in Agile. That means making decisions as we progress. But there was also another opinion that this is not necessarily true in Agile. So that was the discussion about it.
Wow, this is an extremely interesting observation. What can I say here? First of all, at the beginning of the evolution of Unix, so say the first 10 years, it was the decisions were not made earlier. So if we looked at the first 10 years, it was created in an agile fashion. They did not create a system, a large footprint and design from the beginning. This was the Multics idea that failed, but a very small system, just 1,800 lines of code, to which they added things over a period of 7 to 10 years. So until the 7th edition Unix, it evolved in an agile fashion. If we look at it over 50 years, it looks like a lot happened in the first years, but 10 years a long time. So over the large, longer period, it looks like a lot happened at the beginning. But first of all, also many things happened later on. And secondly, that time was split in smaller periods, and it evolved in an agile fashion. They didn't at the beginning create a complete permission framework or hundreds of system calls. There were just very few system calls or even pipes and filters. So it was developed in an agile way. Another thing I would add is that it was a remarkably talented team. So I think we can allow them to create 20 system calls from day one. I don't think that many of us have the same architectural vision and come up with the same brilliant abstractions from day one. So agile is perhaps more important the less we know. Also keep in mind that they had a failure on their backs, which is also valuable knowledge. Agile is a learning mechanism, and they already had something, they learned a painful lesson.
I see. So for me, what was fascinating is that there were so many successful design decisions compared to the size of the code. But it seems that they really did an incredible job at the beginning with respect to the design, or as you have said, one decision at a time, but still really successful design decisions.
Indeed, just in my feeling, I cannot objectively put my hand on it, is that the extreme poorness of resources they had, the restriction on memory, on the way you type, right, on a teletypewriter, or everything you type takes some time to appear on paper in front of you, forced them to think very carefully what was the minimum thing that could be done in order to create a successful system. Initially, Ken Thompson wrote this unnamed system as a way to experiment with files. So he tried to, there's a very interesting paper written by a colleague in Australia based on it, Warren Toomey, and it shows how he struggled to create a fewer system calls that would allow him to save some information on disk and retrieve it. So obviously something like create, read, write, open.
All right. So thanks, Yasmin, for the question. Thanks, Diomidis, for the answer. I actually have a question. We still have a little bit of time. So, Diomidis, I'm thinking about the V-shaped, let's say, trends in the complexity of the code. And do you think there is some, I mean, which were the forces like leading to this decrease of the complexity?
Right. This clearly requires further study. Some things we have seen by looking at code is that some keywords or abstractions were thrown out. For example, the register keyword, void was introduced, and so on. So people periodically went through the code and refactored some things. Goto was reduced up to a level. My feeling, but as I said, it requires further study, would be that in addition to that, what is happening is that we have become wiser through education, through painful lessons, and new code that is being brought in is written better than the code that is existing. So it's not so much refactoring, although refactoring has clearly taken place, as witnessed by the reduction of old features and the introduction of new language features. But also because the new code is better than the old code.
All right, that's a good one. I was actually thinking more about maybe they were driven by some performance problems and then they refactored in some way, but maybe, yeah, we need to do a study about that.
Exactly. And I'm open to collaborations on this.
All right. Thanks. There is a last question by Roberto. Roberto, if you want, you can unmute yourself and do it.
Yes. Hi. I just was curious. The high-level architecture view we see in the slides, was it taken from the manuals directly, or was it reverse engineered from the source code?
It was reverse engineered from the source code and the knowledge I have on Unix. Haven't worked on it for a number of years. I have in mind the architecture. There are books that describe it. The manuals do not contain an architecture, but their division in those 9 sections clearly sets the boundaries: user commands, administrative commands, library, kernel, and the lower systems are visible from the source code in the form of directories and subdirectories. Plus, as I said, there are at least two books that describe the architecture of Unix, the ones created by the Berkeley authors and the ones created by Bach on the AT&T versions.
Okay. So to test my knowledge, first you went to the manuals and then at the finer grain level to the source code.
Exactly.
Just
Mainly
to double check what you had found in the manuals and put the
go at the lower and provide more detail. The manuals give us a very rough division. The large boxes I included. The smaller boxes are source code in the form of directories and subdirectories mainly. This is the main unit of modules used in the C language that Unix is implemented in.
Thanks.
All right. So since it's 9:45, and yeah, sorry, Yasmin, I'm seeing your question, but I need to close the session. So there is a channel for a further discussion. So take this as a chance to continue a discussion in the channel. So thank you. Yes, thank you, Diomidis, again for the very interesting keynote.
Thank you very much for the invitation. I will move to the channel and try to answer questions there.
All right. Okay. Thank you very much.
Bye-bye.
Thank you, everybody, for attending it. Bye.
It was like